All right, so in calculus, we're always talking about slope, right? Is the curve going up? Is it going down? But, that's only half the story. What about the shape of the curve itself? Is it bending gently, or is it taking a super sharp turn? Well, today, we're going a level deeper. We're moving past just the slope to really get a feel for the bend, the curvature of a function. So, let's jump right in.
Okay, picture this. You're on a roller coaster. Now, it's not enough to just know if you're going uphill or downhill, is it? Nah, you want to know how it's curving. Is the track bending up, that feeling where your stomach just drops? Or is it curving down as you fly over a hill? That feeling, that specific bend, is what we call concavity. So the big question is, how do we actually describe that with math? That's what we're going to figure out right now.
So, we're going beyond the slope. The first derivative tells us about increasing and decreasing, which is great. But to really understand the bend, we need a whole new tool.
And here it is, our secret weapon, the second derivative. And honestly, it's exactly what it sounds like. You take the derivative once, to get the slope, and then you just do it again. But here's the key thing to wrap your head around. The second derivative isn't measuring how fast the function is changing. No, it's measuring how fast the slope is changing. Think about it. Is that slope getting steeper and steeper, or is it starting to flatten out? That's the secret the second derivative tells us. It's pretty cool.
The best way to think about this thing is as our official bend detector. The sign of the second derivative, whether it's positive or negative, is going to tell us everything we need to know.
Okay, this comparison is just perfect for understanding the two kinds of bending. So on the left, you've got concave up. Just think of it like a cup, something that could hold water. See how it bends upwards? Now, if you were to draw tangent lines anywhere on that curve, they'd always be below it. And why is that? It's because the slope itself is constantly getting bigger. It's increasing. And an increasing slope means, you guessed it, a positive second derivative. Now look at the other side, concave down. It's the total opposite. It bends down, kind of like a hill or a mound. And here, the tangent lines are always sitting above the curve. That's happening because the slope is decreasing, which tells us the second derivative has to be negative. Simple as that.
So a curve can bend up, and it can bend down. But that brings up a pretty obvious question, right? What happens at the exact moment it switches from one to the other? Let's go find that tipping point.
So you've got a curve bending one way, and then it starts bending the other way. What do you call that exact spot where it switches over? That little point of transition?
That special spot is called a point of inflection. And listen up, because this part is super important. For a point to be an inflection point, two things have to be true. No exceptions. First, the second derivative, y double prime, has to be 0 right at that point. That's like our initial suspect. But, and this is a big but, that's not enough. You also have to prove that the concavity actually changes there. That means the sign of the second derivative has to flip from positive to negative or from negative to positive on either side of that point. You need both. Both conditions have to be met or it's not a point of inflection, period.
Okay, enough theory, let's make this real. We're going to take a look at a classic example, y equals x cubed plus x. Let's go hunt for its point of inflection. All right, first things first, we need that second derivative. So the first derivative, y prime, is 3x squared plus 1. Easy enough. Now we take the derivative of that, and we get our second derivative, y double prime, which is just 6x. Okay, so where could a point of inflection be hiding? Well, we set that second derivative to 0. 6x equals 0. That only happens at one spot, right? When x is 0. So x equals 0 is our prime suspect.
But remember, being 0 isn't enough. We have to check for that sign change. And this little table makes it super clear. Let's test a point to the left of 0. How about x equals -1? We plug that into our second derivative. 6 times -1, which gives us a negative number. That tells us the curve is concave down over there. Okay, now let's check the other side. Let's pick a point to the right, like x equals +1. We plug that in, 6 times 1 is positive, so on this side the curve is concave up.
So, let's recap. The second derivative is 0 at x equals 0, and its sign flips from negative to positive as we pass through x equals 0. We've met both conditions. Boom! We can say for sure that this function has a point of inflection at x equals 0. We found it. All right, now for something really cool, a special case. What happens when a point of inflection shows up at the exact same place as a stationary point? This is where it gets interesting.
This is what we call a horizontal point of inflection. It's this amazing point where the curve does two things at once. It momentarily flattens out, so the slope, or y prime, is 0. And at that exact same instant, it also switches its bend, which means y double prime is 0, and it changes sign. It's like the ultimate multitasker of the calculus world, doing double duty.
Let's see one of these in the wild. We're going to investigate y equals x cubed minus 3x squared plus 3x minus 1. Our mission? Find out if it's hiding one of these special horizontal points of inflection.
Okay, we've got a clear step-by-step plan. First step, find the stationary points. We get the first derivative, set it to 0, and we find that happens at x equals 1. Got it. Step 2, find the second derivative and see where it equals 0. We do the math, and what do you know? It's also 0 at x equals 1. Okay, this is looking very promising, but we're not done. We still need that crucial third step, confirming the change in concavity.
And just like we did before, this table lays it all out for us. If we test a point to the left of x equals 1, the second derivative is negative, so we're concave down. Then we test a point to the right of x equals 1, and the second derivative is positive, concave up. The sign definitely flips. That's our confirmation.
So we proved it's a stationary point, and we proved it's a point of inflection, both at x equals 1. This is our special case, and this is exactly why we call it horizontal. Because the first derivative is 0 there, it means the tangent line to the curve at that one spot is perfectly flat. It's horizontal for just a single moment, right as it's changing its bend. Just a moment of perfect stillness right in the middle of all that change.
So you see, the second derivative isn't just some abstract thing we do in a math class. It's a really powerful tool for describing the actual shape of, well, anything. It tells us about the bend, the curve, and most importantly, those critical tipping points, the points of inflection, where the whole personality of the curve just changes. So the question I want to leave you with is this: where else do you see these tipping points out in the real world? Think about the path of a basketball shot or the shape of a suspension bridge. What about the graphs you see on the news about the economy or how a disease spreads? I promise you, once you start looking for them, you'll see these inflection points everywhere. The world is full of curves, and now you know how to read their shape.